Hello guys, nice to see you. How are you doing?
Good afternoon.
Hi. So during last discussion, we introduced Carnot cycle as the most efficient cycle for any thermal like heat engine, which is reversible cycle, means that it can come back to initial set of state parameters, and derived equation for the performance of such cycle, Carnot cycle, which consists of two isotherms and two adiabatic processes. We have shown that the performance of Carnot cycle is defined only by temperatures of the cold and hot reservoirs. So it doesn't depend on the working substance and design of this engine. And a little bit earlier, we also considered the second law of thermodynamics from the point of view of heat engines or heat pump. It depends in which direction these mechanisms are operating. So today we are going to introduce a new state parameter, which is entropy, and introduce second law of thermodynamics in terms of entropy, and to be more specific in terms of change of entropy. We will define quantitatively what is change of entropy, like differential of this state parameter ds, and derive equations which will allow us to calculate the change of entropy for different processes in ideal gas, means isobaric, adiabatic, isochoric, and isothermal processes. So that's our plan for today. And switch to our slides. As I mentioned, entropy is another state parameter, and today we will consider it in the scope of like microscopic scale, as it was first introduced in 1865, and later during our next discussions we will consider already the same state parameter, like entropy, in terms of microscopic approach. So initially entropy was considered as some useful concept in thermodynamics. However, over time its importance was increased, and specifically with the rise of statistical mechanics, which describes behavior of systems with many particles. So, for instance, if we consider some container which is divided in two parts, and one part is filled with gas, another is empty. So at that moment, when we get rid from this wall inside, so we connect two parts of this container, there will be distribution of atoms of this gas all over the container, and it will be evenly distributed all over the volume. There is negligibly small chance that we will have something like this, that all molecules, like atoms of this gas, will move to the second half of the container, or they will be after some time accumulated again in the left part of this container. So this probability is not equal to 0. There is still a chance that it can happen, but this chance is negligibly small. It's just approaching to 0. So most probable distribution under steady state equilibrium conditions will be when molecules evenly are distributed in the volume of this container. And that will correspond to the highest level of disorder in the system, because molecules will randomly locate in all with equal probability in any space, any small volume of this container. And in other words, such equilibrium condition with highest disorder will possess the largest number of microstates which can describe this macro state of thermal equilibrium, which every isolated system want to reach. So if we introduce this entropy as a state parameter, it has direct relationship with disorder. So it's kind of a quantitative measure of disorder in a thermodynamic system. That brings us to the statement of or introduction of second law of thermodynamics in terms of entropy. So if we know that for all isolated systems which do not have any interaction with external environment, over time it tends to reach the equilibrium condition, steady state equilibrium thermodynamic condition. It tends to highest disorder. If entropy, which is denoted as capital S, is measure of disorder, thermodynamic disorder of the system, then means we can write that entropy for all isolated systems under self-governed processes which happen without external impact will either increase or remain constant. So it will be either larger or equal to 0. So actually this is true for change of entropy. Means that entropy itself will either increase or remain constant. So that defines the direction of thermodynamic processes as they can happen by themselves in isolated system. Obviously, it is possible to realize a condition when we will intentionally reduce entropy of the system. That's, for instance, when we operate some heat engine in this heat pump mode. However, in that case, this system is not isolated anymore, and it requires some work done on it from external environment. So that is already a different story. If we have isolated system, all self-governed processes will lead to constant or increased entropy. So constant entropy will be valid for reversible processes, increased entropy for irreversible. Since we know that all natural processes are irreversible, we will observe increase of entropy, and this constant entropy is kind of idealistic approach, which is valid for some reversible cyclic processes like Carnot cycle. We will talk about that a little bit later. So also what is important to mention that entropy is a state parameter, means that change of entropy will be defined only by initial and final state. It will not be defined by the path, how it moves, like goes from the how the system thermodynamically changes its state from initial to final. The path doesn't matter for change in entropy. It will be defined by only by initial and final state. Means that if we have some initial and final state, and there is some irreversible process for system to go from initial to final state, means that we can replace this process by some reversible process or set of reversible processes, which will lead us to the same change of state from initial to final. In that case, we can do calculations of change of entropy, and it will be valid if we consider exchange of energy in terms of heat, which is happening during reversible process. So how we can quantitatively define entropy? Actually, change of entropy has physical meaning because entropy is defined with respect to certain constant, which can be arbitrarily defined. Change of entropy provides us the physical meaning, and change of some parameter is like small change of some parameter is some differential of state parameter entropy ds can be represented as dqr divided by t. So when we have some small change of the system, a change of entropy is defined as amount of energy transferred during reversible process QR in form of heat divided by temperature of the system. So at this case, since we are talking about very small changes in thermodynamic conditions, we can assume temperature as constant parameter and use it here. So that is the definition, general definition of differential of state parameter entropy when we have some reversible process. As I mentioned, if we have some irreversible process, we can substitute it with a set of reversible processes, which will lead to the same change of state from initial to final, and consider this exchange of energy in forms of heat during these reversible processes. Now, what if we want to determine change of entropy, like some large change of entropy, not very small, when thermodynamic conditions experience large changes? So in that case, we need to go to integration. And actually, no, it's not ds anymore. Large change we will denote as delta s. And that will be integral from initial to final state over this differential ds. Or in other way, from initial to final state dqr over t. So why we need to use integration now? That also comes from this temperature. If we have a significant change of thermodynamic condition between this initial and final state, we cannot anymore assume that temperature remains constant. So it also changes. And that's why we need to integrate this expression, which defines differential of state parameter entropy. So let us first consider this reversible Carnot cycle, and we can write that integral along this path of the cycle, which is closed, dqr over t is equal to 0. So that is definition of reversible process in isolated system. Change of entropy is equal to 0. So we can write that large change of, like total change of entropy in Carnot cycle can be defined as QH, amount of heat which system got from the hot reservoir divided by temperature of hot reservoir minus QC, amount of heat which was expelled by Carnot engine towards the cold reservoir divided by TC. So now, if we recall our previous discussion when we derived expression for the efficiency of Carnot cycle, we have shown that the ratio, the absolute value of ratio QC over QH is equal to TC divided by TH. Keep in mind that this is valid only for Carnot cycle. So if we apply this, so this change in entropy will be valid for definition of change of entropy will be valid for all heat engines. But taking into account this ratio, which is valid only for Carnot cycle, applying this to this definition of change in entropy for a cyclic reversible process, we will end up with delta S equal to 0. So that is actually, you can see it because from this ratio, we can write that Q H absolute value divided by TH is equal to QC absolute value divided by TC. So if they are equal, so their difference will be equal to 0. And that's why we show that for Carnot cycle, change of entropy is equal to 0. However, it will be only for Carnot cycle because it's reversible cycle. All other will result in some positive change of entropy, increase of entropy during the realization of this cycle. So this statement delta S is always larger or equal to 0 is actually a formulation of second law of thermodynamics and defines direction of self-governed thermodynamic processes in isolated systems. So what is important that this is also valid in extremely large scales, like universe, for instance. It is actually known that universe is also moving towards highest probability macro state, which corresponds to the increase of entropy, and it's on the way to reach the perfect disorder, which implies that there will be no energy available for doing some work, and means that over time, eventually at the end of universe existence, it will reach to this thermodynamic equilibrium when all energy in atoms and elementary particles, so all these structural like building blocks of matter will actually vanish, and the universe will be just empty space with maximum possible like perfect disorder level. So that this definition of second law of thermodynamics in terms of change of entropy, which shows that it's always increasing for irreversible processes, inside isolated system also defines the development of such a global system as universe. So that is the introduction of entropy as a new state parameter and highlight of its relationship with the disorder of thermodynamic systems and explanation of the second law of thermodynamics in terms of this change of this new state parameter entropy. Now we need to derive some equations which will allow us to calculate change of entropy of ideal gas. So it's a really good reference system for application of different concepts, thermodynamic concepts, and that's what we are going to do now. So we will consider 4 different thermodynamic processes in ideal gas. Means we will start from isobaric process. So why we start from isobaric? Because during isobaric process, as you remember, by the way, do you remember which parameter stays constant during isobaric process? Any suggestions? So isobaric process, that is constant pressure. We have isothermal process, which is constant temperature, isochoric process, constant volume, and adiabatic process means no energy exchange in form of heat between system and environment. So all these 4 processes we will consider and derive equations for change of entropy. So why we start from the isobaric process? Because during isobaric process, we experience change in all parameters in terms of internal energy, heat, energy transfer in form of heat, and also work. First we consider here P is equal to constant. And change in entropy, like differential of the state parameter entropy, we know that it's defined as dq over T. And we can write that it's 1 over T. D, change in internal energy, and also work done by the system. So we can express change of internal energy in terms of specific molar heat capacitance times number of moles of ideal gas. So CV times nu times delta T. Actually 1 over T we forgot here, so we have parentheses. And then we also need to do something with this constant pressure P. We can recall the equation for the state of ideal gas. PV is equal to nu times R, universal gas constant, times temperature. From here, we can write expression for the pressure will be nu times RT divided by V, and substitute this instead of pressure here. So we will get nu times RT divided by V times dV. Now, if we open the parentheses, we will get CB times nu times dt over T plus mu times R. Temperature in the numerator will be canceled because of this temperature in front of the parentheses, will be times dV over V. So these are two components which define the differential of entropy. First component responsible for the change of temperature, and other component responsible for the change in volume. So now when we want to find the change of entropy between two states, delta S, that should be equal to integral from initial to final state of this differential dx. That is equal to, since CV and mu are constants and nu and r are constants, they will be taken out from integrals. So the CV times nu integral from t initial to t final dt over t plus nu times r integral from v initial v final dv over v. So now we recall that from table of integrals that integral of dx over x is equal to natural logarithm of x. We can write that this will be equal to CV times mu times natural logarithm of t final divided by t initial plus mu r natural logarithm of v final divided by v initial. So this we keep in mind, and probably let us write it on the next slide so we can consider further with transformation of this equation. So we go to next slide. Change in entropy is equal to CV times nu natural logarithm of t final divided by t initial plus nu times r natural logarithm of v final divided by v initial. So with this, we can proceed further. As you remember from our previous discussion, CV for ideal gas, assuming that we have only translational motion, means monoatomic gas, is equal to 3/2 times R, universal gas constant. So this we remember. And also for isobaric process, the ratio of volume to temperature remains constant. Means that V1, or let's say V initial to T initial is equal to V final to T final. From here, we can write that the ratio of V, or maybe let's start from temperature, T final to T initial is equal to V final divided by V initial. As you see, we have these ratios in the arguments of our natural logarithm, and they are equal to each other. So we can substitute them in any way we want. So taking this into account and the fact that CV is equal to 3/2 times R, let us substitute it and see what we get. Delta S, change of entropy during this isobaric process, will be equal to 3/2 nu times R, natural logarithm. So here, instead of temperature, we can substitute, for instance, a ratio of volumes. So V final divided by V initial plus nu times R, natural logarithm of V final divided by V initial. So now we can take out of parentheses nu times R times natural logarithm of V final divided by V initial. And we will have here 3/2 plus 1. So eventually, for monoatomic ideal gas, change of entropy during isobaric process will be equal to 5 seconds times nu R natural logarithm of V final divided by V initial. We can represent it also in a bit different form, which can be useful for applications at some conditions. We can write the following. It will be 5/2 nu times R, natural logarithm of V final we can express as V initial plus delta V divided by V initial. So in that case, we can express this change of entropy in terms of change of volume divided by initial volume. So it will be 5 seconds nu times R, natural logarithm of unity plus delta V divided by V initial. Okay, so we have this equation for the isobaric process, and we need to proceed further and get equations for the adiabatic, isothermal, and isochoric process. On the next slide here on the top, we will just write down expression for the differential of entropy, which is equal to CV times mu times dt over T plus mu times R dV over V. So we keep this in mind and we will proceed further. So first, let us consider the most simple case. It's adiabatic process. We know that dq is equal to 0. There is no exchange of energy in form of heat during adiabatic process. And that's why delta S is equal to 0, 2. Because ds is defined as dq divided by T. If dq is 0, then ds is also 0. Now let us consider isothermal process. T is equal to constant. In this case, T initial is equal to T final, and integral of dt over T from T initial to T final will be equal to 0. Means this contribution to the change of entropy responsible from change of temperature in the system will be equal to 0. So that will be defined only by the second term, and change of entropy delta S will be equal to mu times R, natural logarithm of V2 divided V final divided by V initial. Or as we described earlier, can be mu times R, natural logarithm of unity plus delta V divided by V initial. So that is valid for constant temperature for isothermal process. And we have one more process, which is isochoric process. in isochoric process, volume is constant. Again, V initial is equal to V final, and integral of V initial from V initial to V final dV over V is equal to 0. So contribution from this term responsible from change of volume obviously will be cancelled. So in this case, change in entropy delta S for isothermal process. So here we can write V constant. No, that is for isothermal constant. The temperature is constant. And here isochoric process is volume constant. Change of entropy for isochoric process will be Cv times nu times natural logarithm T2 divided T final divided by T initial, or Cv times nu natural logarithm of unity minus delta T over T initial. So here Cv will depend on the degrees of freedom for ideal gas. So it will change from C3 half to for translational motion of monoatomic molecules, or translational motion of diatomic molecules when temperature is equal to like small values. So if at low temperatures, if we have diatomic ideal gas and temperature increases, then we need to take into account rotational motion of these molecules, which will increase value of Cv to 5½ of times R. And even at higher temperatures, when also vibrational motion is activated, another 2 degrees of freedom can be added, so it will be 7½ times R. So that is factor which will depend on the structure of ideal gas molecules and also temperature range. So with this, I would like to summarize. So today we introduced the concept of new state parameter entropy, which is a quantitative measure of disorder. So in isolated system, on the way to thermal equilibrium condition, self-governed processes cause increase of entropy, or this entropy remains constant if the process is reversible, but since all processes are irreversible, entropy always increases. That defines the direction of thermodynamic processes and can be considered as a formulation of second law of thermodynamics. We derive equations for the change of entropy in ideal gas during different thermodynamic processes, started from isobaric process, because there we see changes in internal energy, heat, and work done. So we have all 3 components. And after that, once we derive this for isobaric process, it's easy step-by-step change from isobaric process, which includes all changes, to other processes which exclude certain contributions. For instance, adiabatic process, we don't have heat exchange, then it change of entropy is equal to 0. And for isothermal and isochoric processes, we do not have contributions to the change of entropy associated with change of temperature and change of volume respectively. So based on that, we obtain equations for change of entropy for all these important processes in ideal gas, and they can be used for practical applications. So with this, I would like to finish our first part of discussion of entropy. If you have any questions, you are welcome. We will continue our discussion of entropy next lecture also, but already from more microscopic point of view. So that will be our goal for discussion on Wednesday. Okay, guys. Then thank you very much for attending. Have a good day and take care. There will be also 6 problems in final exam. You have the same amount of time dedicated for final exam. Will be early next week. So we will definitely send you an email. We'll see when we have this all prepared. We will contact you, let you know when it's scheduled.
Thank you. Bye.
Okay, thank you for attention. Have a good day and see you next time. Bye-bye.
Goodbye.
Bye.